Hello, my name is Ben Ruppig from Heinrich-Heine University Düsseldorf, and I present to you our work called Less is More: Local Intrinsic Dimensions of Contextual Language Models. In training a large language model, we teach it to produce a contextual embedding space in high dimensions. In general, this is an expensive process, so you want to get it right. And for evaluation, most performance diagnostics in LLMs rely on supervised validation or task-specific probes. We still lack a geometric understanding of what happens inside of the embedding spaces. The structure of these embeddings governs how information is represented and processed. In our schematic figure, the black dots represent individual token embeddings. Remember that the same token used in a different context can produce a different embedding vector. We ask whether we can uncover model behavior purely from the structure of its embedding space. More generally, during training, can structural changes in the embedding space yield unsupervised insights into model behavior across language modeling tasks? We approach this by quantifying how the local structure of embeddings changes during training. For example, if the model learns to compress the embedding space, like in this schematic, we hope to pick this up via measuring the local dimension. Specifically, we apply a localized version of the 2NN estimator to subsamples of the token embeddings. This quantifies the local intrinsic dimension throughout the space. While the ambient dimension of the contextual embedding spaces is typically large, ranging from hundreds to thousands of dimensions, our observations show that the local intrinsic dimension reflects the lower dimensional structure, in the order of tens, which varies across data space regions. This heterogeneity allows us to derive model and data-specific geometric signatures by looking at the dimension distribution. This is without relying on labeled validation data or task-specific supervision. We present a unified framework for analyzing LLM training dynamics through the mean local dimension. I will now go on to present our main findings in different model training settings. First, we note that fine-tuning leaves a geometric trace in the local intrinsic dimensions in a dataset-specific manner. The mean dimension drops on training data used for fine-tuning, while it remains largely unchanged on unrelated data. This can lead to conclusions on shared data across tasks. Next, we can detect grokking, which is where a machine learning model acquires specific skills only after extended training far beyond overfitting on the training set. Here, we learn an arithmetic operation in a small group, and before the model begins to generalize, its embedding geometry already hints at the phase transition in grokking when the dimension starts dropping. In settings where the model does not grok, the mean local dimension keeps increasing. Next, we demonstrate that local intrinsic dimension can predict training convergence, as in this sequence tagging-based dialog state tracking task. Here, the validation loss starts increasing, while train loss keeps decreasing, and one would erroneously conclude that further training is not beneficial from this point. But looking at the mean local dimension, which keeps dropping, we get a hint that we should continue training, and indeed, the downstream task performance still increases. Later, the stabilizing mean dimension correlates with model stabilization. Finally, we can also detect overfitting in the sequence classification task. Here, the validation loss increases quickly, and we are indeed overfitting when we are looking at the downstream task performance. In the local dimensions, this is reflected through an initial drop, followed by a rise in dimensions, which mirrors the model's trade-off between generalization and memorization. To summarize, we can now study learning through geometry, reducing our reliance on task-specific validation. A sustained drop in mean local dimension reliably predicts improved generalization. By revealing this hidden geometry of LLMs, we take a step towards making training more interpretable, transparent, and manageable. Thank you very much for your interest, and for more details, follow the links on screen to find our full paper and code.